So as of now, the session is being recorded. Good afternoon. Welcome to another episode in chemistry, organic chemistry to be specific. All right, today there are a couple of things that we want to address, we want to look at. Firstly, we would recap some things from last class, and then we would, all right, so anyone just logging in, please mute your mics. Excellent, excellent. All right, so we're gonna first recap some of the things from last class before we move forward. All right, Dimitri, can you hear me? All right, good, nice. Jesse, you can hear me? Jesse, can you hear me? Yes, excellent. So everybody could hear me. All right, wonderful. All right, so today all right, Bridge Mohan, I see you too. Excellent. I'm glad we're all hearing each other. Okay, so if you have a question or anything, you could always raise your hand and let me know. All right, or you could type it in the chat. I'll take a look at the chat and I will answer the question. All right, so today's class, we talking about organic chemistry, right? The objectives that we're trying to cover today. Firstly, I'll recap some of the things from last class that we did, and then move forward to what I want to cover in today's class. All right? So let's get right into it. All right, so the first set of objectives that I want to look at is objective 14.1 from your syllabus. All right, that's name and draw the structure of methane, ethane, and ethanoic acid, and also be able to name and draw the structure of the unbranched alkane alcohols, and alkanoic acids. Thirdly, state the type of compounds present given a chemical name ending with ANE, ENE, OL, oic acid, and be able to name and draw structural formulae of the esters which can be made from unbranched alcohols and carboxylic acids. All right, so when naming compounds, there are two basic things that we need to consider. First, you have to consider the prefix as well as the suffix, right? You have to consider the prefixes as well as the suffix. So it's like, sir, what you talking about? When we talk about the prefixes from last class, we are talking about met, et, prop, but, and we went all the way up to 10. 10 carbons. Met represents 1 carbon, et represents 2 carbon, prop represents 3 carbon, and but represents 4 carbons. Right? So each of them represents a carbon number. Et is 2, met is 1, and so on. All right. So moving on. And when we talk about the suffixes, so far we have looked at the suffix for alkanes, which end in ANE. Alkanes, the ones that end in ANE. Now, alkanes have only single bonds. Alkanes have only single bonds and not double bonds or triple bonds. They only have single bonds. An example of an alkane is ethane, butane, propane, methane. These are all examples of alkanes. Now the suffix is the last part of the alkane, which is ANE. Right? The suffix is the last part of the alkane, which is ANE. Now the other three groups that we need to look at are alkenes, which have the suffix ENE. Right. Excellent, thank you. All right, so the alkenes end in ENE, Alcohols end in OL, and carboxylic acids, they end in anoic acids. Right? So example of an alkene is ethene. Example of an alcohol is ethanol. Example of a carboxylic acid is ethanoic acid. Now, ethanoic is only one example. We could have used propanoic, we could have used butanoic, we could have used pentanoic. All these would represent carboxylic acids. So let's take a look at something that we looked at last class. So as I'm telling you, I am recapping first some of the things that we went through last class before we move forward. Right? So methane, which is an alkene, have the formula CH4, right? That's the molecular formula. And it has a displayed structure of one carbon that is bonded to 4 hydrogens. And the reason why this is possible is because carbon is tetravalent, right? Carbon is tetravalent. There's one carbon that is bonded to 4 hydrogens. And because of that, this carbon right here is tetravalent. Tetra meaning 4, so there are 4 valence electrons, and there are 4 electrons that can come and bind in the outermost shell. Right? There are 4 valence electrons, and then there are 4 that can come and bind in the outermost shell. All right, so then we have ethene. Ethene has the molecular formula C2H6, and the structure or displayed formula, you see in the 2 carbons, and each carbon has 3 hydrogens that is bonded around it. If you look very closely, if you look at it, you'd see that each one has 3 hydrogens bonded. So this carbon has 1, 2, 3 hydrogens, and the second carbon have 1, 2, 3 hydrogens. Attached to it. All right, so moving on. We have ethene. Now, ethene, the suffix of ethene is ene, meaning to say that we are dealing with an alkene, not an alkane. So therefore, et represents 2 carbons. Et represents 2 carbons, and ene means that we're dealing with an alkene. So therefore, that tells us that we have the presence of a double bond. Carbon is double bonded to another carbon. When we have a compound that ends in ene, it tells us that it is bonded to a double bond. Oh, my mic is breaking up. Oh, Jesus. All right. Is it still breaking up? Just maybe relocate a little bit. All right, good now. All right, cool, cool. All right, so I'm saying that with ethene, we have 2 carbons present, and there's a double bond that is present in between those 2 carbons. Right? A double bond is present in between those 2 carbons. There's a double bond that is present right here in between those 2 carbons. Right? With ethanol, it has the presence of an OH group. Et means, again, there is 2 carbons, and it ends in OL, means that there is an alcohol group. That OH group represents the presence of an alcohol. So the molecular formula is C2H5OH, but the displayed formula is 2 carbons. The first one is bonded to 3 hydrogens, the second one to 2 hydrogens, an oxygen and a hydrogen. Then we have ethanoic acid. Ethanoic acid, an acid is represented or identified by its functional group. This C double bond OH group here This helps to identify the presence of ethanoic acid or a carboxylic acid. This C double bond OH, it helps us to identify the presence of an acid. Now, we will get into that later when we reach the carboxylic acids. But for now, we just want to see how we can identify the molecular formula. For ethanoic, there are 2 carbons. X represents 2. So you have CH3, which is 1 carbon bonded to 3 hydrogens. Then there's the second carbon that is bonded to 2 oxygens. One has a double bond, the other has single bond, which is then bonded to hydrogen. So that C double bond OH group is the functional group that helps to identify a carboxylic acid. So from your objectives, you need to be able to state the type of compounds present, give a chemical name ending in ANE, ENE, OL or oic acid, or a molecular structure that we just embarked upon. So ANE represents alkanes, just to go back over it. ENE represents alkenes. OL represents the presence of an alcohol, and oic acid represents the presence of a carboxylic acid. The functional group for the alkanes is not C double bond C. It is carbon bonded to a single carbon, or if you wanted to say carbon bonded to hydrogen, that might be accepted as well. All right, for alkenes, it's carbon double bonded to another carbon. For alcohols, the functional group is a OH group, while for acids, the functional group is C double bond O, OH. Which takes us to the next thing that we want to talk about. Names and drawing the structural formula of the ester, which could be made from unbranched alcohols and carboxylic acids. Jesus. All right, so an alcohol, generally speaking, an alcohol plus a carboxylic acid normally gives you an ester plus water. An alcohol plus carboxylic acid would normally give you an ester plus water. So you could have what is called methanol, for example. Methanol is an example of an alcohol. Methanol plus ethanoic acid would give you methyl ethanoate plus water. An alcohol plus a carboxylic acid gives you an ester plus water. So how did we come up with that name, methyl ethanoate? What they did, they took the prefix of the alcohol, and they add YL to the word. They took the prefix of the alcohol and they add YL to the word. Then the name of the carboxylic acid, they took that name, they removed oic acid from it, and they added O8 to it. So we ended with, instead of methanol, they took off the anol and they added YL to the prefix. Meth, and they add YL, which made it methyl. And then for ethanoic acid, they removed the oic acid and they added OATE, which made it ethanoate. So you ended up getting methyl ethanoate plus water. That methyl ethanoate is your ester. The methyl ethanoate is your ester. Right? So this is an example of what the structure would look like if I had methanol being added to ethanoic acid. If you can look clearly, you would see that the acid part is written before the alcohol part. So this part over here is your acid part. This would have been taken from the acid, and then the part on the other side would have been taken from your alcohol. However, when you're writing it, you write the name of the alcohol part first, followed by the name of the acid part. Hence, instead of getting ethanoate methyl, they wrote methyl ethanoate. All right. So just to open it up so that you can actually see how it's happening. The methanol lost hydrogen. So methanol, met represents the presence of one carbon, and it has an OH group, meaning that it's an alcohol, while the ethanoic acid, et represents the presence of two carbons. Right? Et represents the presence of two carbons. So on this side here, we have, for methanol, we have the presence of one carbon. And on the other side, over here, we have two carbons present. So, that's supposed to come back there. All right. How do we erase? Okay, solve problem. Okay, so on this side here, we have the ethanoic acid, and ethanoic acid is losing the OH group from the C double bond OOH. So the OH group here is being lost, while from the methanol, the hydrogen is being lost. So H plus OH gives you H2O. So you have the formation of water. Hence, water is formed on the opposite side. All right? Water is formed on the opposite side. Okay, just 1 minute. All right. Yes, so the compound or the product that is formed is an ester, which is methyl ethanoate, and methyl ethanoate, and that is a ester. Right, so I found different ways to try and represent it visually for you guys to see. When we had ethanoic acid to an alcohol, an acid plus an alcohol gives you an ester plus water. And that process is a condensation process, right? Meaning to say that water is given off. Condensation, water is being liberated. Now, if we were going in the reverse direction, we will take an ester plus water and it undergoes hydrolysis. We would produce an alcohol plus an acid. But right now we're just looking at the acid and the alcohol coming together, and that gives us the ester plus water. Right? So this here is just putting in words what we have just said. The alcohol part is normally to the right with a hydrogen from the OH functional group being lost. And the carboxylic acid part is to the left with an OH from the C double bond OH functional group being lost, right? Which is this what we were talking about here. The H from the OH group is being lost, and the OH from the C double bond OH group is being lost. Right, that results in the production or the formation of a byproduct that we call water. All right, so different carboxylic acids, different alcohols, if we were to look at them to see the ester that is formed, we could start with methanoic acid plus ethanol, and what it gives us is ethyl methanoate. Ethyl because they took the prefix from the alcohol and add YL to it, and then they remove oic acid from the methanoic acid and they add OATE to it. Oh, Jesus, the mic's still breaking up. Oh, my Lord. I think it's my internet connection. I have T-Mobile. That's so bad. I should get Flow. I probably should. Okay. All right. Is the mic better now? Can you hear again? Or is it still breaking up? All right. Okay, very well. Okay, so if we were to take ethanoic acid and methanol, we're looking at the second example that we have. From the methanol, you're taking out the prefix met and you're adding YL to it. From the alcohol, you take out the prefix and you add YL to it. From the acid, you're taking out OIC, oic acid, and you're adding OATE. So ethanoic acid plus methanol becomes methyl ethanoate plus water. Right, now if we go on to try the next one, if we add propanoic acid plus ethanol, from the ethanol, you're going to take out the prefix eth and add YL to it. It becomes ethyl. And then from the propanoic acid, you're taking out the oic acid and you're adding OATE to it. So it becomes propanoate. So you end up with ethyl propanoate, right? And that is your ester plus water. And if we look at the fourth example, we have butanoic acid plus propan 1-ol. Now the 1 in the propan-ol tells us the location of the OH group. The 1 in the propan 1-ol tells us the location of the OH group inside of propanol. Right? We will get to that when we start talking about alcohols, but that's just for your knowledge sake. Again, with the propanol, we take out the prefix, which is prop, P-R-O-P, and we add YL to it, right? Which gives us propyl, C3H7. To the butanoic acid, we remove oic acid, OIC, ACID, and we remove the oic acid from the butanoic acid, and we add OATE to it. So it becomes propyl butanoate. It becomes propyl butanoate. All right, so at this point, you could hear good, excellent, excellent. At this point, I have a short little video that I want to play for you guys. You let me know if you're hearing the audio when I press play, and if not, then we would fix that so you can hear.
In this video, you will learn how to use different types of formula to represent organic molecules. The formula used most frequently in our videos has been the displayed formula. This is because displayed formula provides the clearest visual structure of an organic molecule. Here is the molecule butene, showed in displayed formula. It shows all the atoms in the correct order with lines to represent all single and double covalent bonds. Drawing all the bonds for very common molecules can be quite repetitive. For example, here is butanoic acid in its displayed formula. Since this is a common molecule, and as chemists we are clear with the bonding arrangement of carboxylic acid functional group, we also use structural formula to represent organic molecules. Here is the structural formula. As you can see, the covalent bond between the OH is not showing, as we know this arrangement anyway. In fact, we could simplify this further and remove all the displayed bonds like this. Structural formula is often used when writing equations, but the formula doesn't mean that it's always clear what arrangement bonds are in. Here is another example. First, the displayed formula of propane. If we then take out the lines representing the covalent bonds and group our atoms together in order they are arranged, we make the structural formula of propane. Pause the video now and try and draw both the displayed formula and structural formula of pentane, which has 5 carbon atoms.
Alright, so would be able to see what you draw. Oh man. Alright. Well, I hope that you try to draw something in your book in the meantime.
Here is the displayed formula of pentane, and here is its structural formula. Molecular formula is another type used and shows us only the number of each type of atom in the compound. To work out the molecular formula, you simply add up each type of atom. For example, here is the displayed formula of hexane. As you can see, it has 6 carbon atoms and it has 14 hydrogen atoms. The molecular formula of hexane is therefore C6H14. This alone is not very useful, as it does not show us how the atoms are arranged and where the bonds are. If you look at these molecules, they all have 6 carbon atoms and 14 hydrogen atoms. Although you may not be able to name these different molecules, you can see they are very different, but all have the same molecular formula. This is the molecule glucose. Pause the video now and complete the molecular formula for glucose. You should have counted 6 carbon atoms, 12 hydrogen and 6 oxygen atoms, so the molecular formula is C6H12O6. Sometimes the formula is reduced even further to make an empirical formula. The empirical formula is the simplest whole number ratio of atoms in a compound. We need to find the highest common factor, that being the largest whole number that is a factor of 6, 12 and 6 in this example of glucose. They all divide by 6. And so if we do this, we get C1H2O1. We don't show the ones, and so the empirical formula is CH2O. Although empirical formula doesn't show us the molecule or how it is arranged, it does tell us the ratio of atoms in the molecule. Now, at the end of this video, you should understand how to draw organic molecules in displayed, structural, molecular and empirical formula.
Alright, so basically what this basically what this is telling us is that there are different ways of representing an organic compound, right? There are different ways of representing an organic compound, right? It can either be a displayed formula where you actually see the carbons and the hydrogens that are present. It could be the molecular formula where it tells you the actual number of carbons, hydrogens, and oxygens. It could be the structural formula, which is a condensed version of the displayed formula. And we can have the empirical formula, which is the simplest whole number ratio. So again, I'm going back. We could have the displayed formula, which is the actual layout of each carbon, each hydrogen that is present, displayed formula, the actual orientation or location of each carbon and hydrogen, or we can have the molecular formula. The molecular formula tells us the exact number of carbons and hydrogens that are present inside of that organic compound. The structural formula is a condensed version of the displayed formula. So if you were to look at what is on your screen, you would see that you have CH3, which is the first carbon and the first 3 hydrogens. Then you could have the next carbon with the next two hydrogens. Then you could have the third carbon with the next two hydrogens, and so on. So each carbon is identified with the number of hydrogens that are attached to it. That is giving you a condensed version of your displayed formula, and we call that your structural formula. Then we have the empirical formula. The empirical formula is the simplified version or the condensed version of the molecular formula. All right, so with that in mind, let us take a look at a question. Right, we have a nice little question here. And the question is saying, the structure of 6 organic compounds are shown. And they tell you, they give you A, they give you compound B, compound C, compound D, compound E, and compound F. And then they ask you to give the name of the compound F. So, anybody have any ideas? What is the name of compound F? All right, so I am sure that by now you would say, I figured it out. There are 4 carbons present, so that's met et pro bute. So it should be bute, and then we have no double bonds, so it should be an alkane. So that makes it butane. So the name of compound F should be butane. So if you got butane as your answer, then that is correct. Right? The name of compound F should be butane. Right? Because there are 4 carbons present and there are no double bonds present. Which means to say that if there are 4 carbons, the prefix that will go with it is bute, and the suffix that goes with it is the suffix for an alkene. Okay, so next. All right, so I tried to put in some of the answers for some of the questions as I was pulling them from the different past papers and stuff to try and allow us to get through as much work as possible in the little bit of time that we have. So well, as you look through, what you see in green on your screen is a reflection of the expected answers inside of the questions that I put. So this part B of the question is identify 2 of the compounds that are members of the same homologous series. Give the general formula of this homologous series. So if we go back to 17 and we look, we can see that A has a double bond and B has a double bond. So A and B both belong to the same homologous series. They belong to the same group. And if we go down and we look at E only have single bonds and F only have single bonds. So therefore, E and F also would belong to the same group. When we have a double bond present, it tells us that it is the presence of an alkene. And when we only have single bonds present, it tells us that there is the presence of an alkane. The general formula for an alkene is CnH2n. So if we had A and B was the choice that we chose, then the general formula for an alkene is CnH2n. But if we chose E and F, then the general formula would have been CnH2n plus 2. Question part C, which 2 compounds are isomers of each other? Explain why they are isomers. Now, as we go down further, we will come across what isomers are, but just to let you know, an isomer Isomers are atoms of the same element, right? They have the same molecular formula. So it means to say that they contain the same number of atoms of each element, but they have different structural formula or different arrangement. So they're asking you, which two of these compounds have the same number of carbons, same number of hydrogens, but they are arranged differently? That's what they're asking you. Which two of the 6 elements, the 6 compounds that they have there, which two of them have the same number of carbons and hydrogens, but have a different arrangement? And if you were to say E and F, you would be correct because they both have 4 carbons and only single bonds. So they have the same number of hydrogens, same number of carbons. So they are isomers of each other. Compounds E and F are isomers of each other. Next question. A hydrocarbon has the following structure. So they show you a structure where carbon is bonded to 4 other carbons and there's a hydrogen bonded all around. And they ask you to state the molecular formula and the empirical formula of this compound. Now, if you recall, when we talk about the empirical formula, it is the simplest whole number ratio. So the molecular formula would be the actual number of carbons and hydrogens that are present. All you do, you count up the number of carbons, which is C4, and you count up the number of hydrogens, which would be 1, 2, 3, 4, 5, 6, 7, 8. So you end up with C4H8, right? And that's your molecular formula. But when you talk about the empirical formula, that is CH2. The reason for that, if you take the C4 and you divide that by 4, you'll end up with 1. And if you take the 8 and you divide it by 4, you'll end up with 2. Because 4 could go into 4 and 4 could go into 8. So we could break it down as much as possible, and that will give us CH2 as our empirical formula, which is the simplest whole number ratio. Now, the next part of the question that follows says this: draw the structural formula of an isomer of the above hydrocarbon. Right now, the answers that they're looking for you to either draw methyl cyclopropane, but1-ene, or but2-ene, or even methyl propene. Now you might say, so how you expect me to know that? I don't expect you to know that right away, right? So please don't be perturbed, right? I have provided the structures for you to see what it would look like, right? Remember, the purpose of this is for you to see it before we go into it and before I give you the questions for you to try and see if you will get the same thing when you start to do it. So the first one, methyl cyclopropene. Methyl is a CH3 group. So on the end of the structure, you have a CH3 group. So right in the corner here, there's a CH3 group right here. And this is connected to a cyclo group. And there are 1, 2, 3 bonds present. Now, this here is a cyclopropene. When we come to cycloalkanes and alkenes, I'll explain this further, right? However, when we go down here, the next option we have is but1-ene. But meaning that there are 4 carbons present, 1, 2, 3, 4. 1 meaning that the double bond is between the first and the second carbon right here. So that makes this but1-ene because there is the presence of a double bond. So it's but1-ene. But2-ene, but because there are 4 carbons present. 2 meaning to say that the double bond is on the second and between the second and the third